Well, we'd like to thank you for the opportunity which we have to present our process control work in sailboat controllers. I've been sailing for over a decade now, mostly boats of small to medium size. And so I have a lot of experience working with sails and rudders and getting from one place to another, which is really what sailing is all about. I know that many of you have probably not sailed on a sailboat before, and so you might think, why on earth would I go out on the open water where there's sharks and big waves and tsunamis if there's not even a motor on the boat? How am I supposed to get back if all the wind stops? But I'd like to assure you, and hopefully our project will assure you, that sailing is safe, this controller is safe, and that everything is going to be okay. And you should try sailing because it's a very fun recreational activity. The objective of our project is, as you might imagine, to control the sails and the rudders to move our sailboat from one location to another. It also, kind of a secondary goal, was to simulate the sailboat and see how water and wind would interact with it in moving from one place to another.
So the purpose of this project is to create a simpler sailboat, the controller, to move sailboats to the one set point by changing tiller and sail angle depending on the current and wind. So after that, so we tune and testing the controller by moving the sailboat from one position to the other. And so our wind is flowing to the northeast and the water is flowing to the southeast. That is the conditions for our control.
So before we get into kind of the results of our test, we kind of wanted to open up the hood and show you what our controller actually looks like. So this might seem like a lot of boxes, but it's a Simulink model that simulates the boat, the wind, and the water, which are the three main components of any sort of sailing system. So kind of a few fun things is right in between where the boat and the wind interact is, as you might expect, our sail here. Also, it's kind of cool that the spatial, you think of a boat and the wind interact through the sail, and also in the Simulink model, right at the intersection between those two is where the sail control is. Our boat design, a few interesting things is that we're constantly having to change between vectors and these angles, because the rudder really thinks about things in terms of angles. It changes the angle that the boat is going. But what we really care about is getting to a destination, which is kind of an X and a Y coordinate, you might think. And so what we're constantly doing is we're constantly measuring what our position is and what direction the boat is going, and using that position we're at and our final set point location to get a sort of ideal angle we would be traveling. And then using that difference between the angle we're currently traveling and our ideal angle of travel to modify our rudder position. And that's what's happening here in this. It says PID, but it's actually a P-only controller for the rudder right there. Also, an important thing to know is that this is an integrating system. If you just move the rudder to one side, you're constantly going to be changing the angle. It's never going to be reaching a set point in angle traveled. It's the same thing with location. If you're constantly moving in one direction, you're never going to reach a set point destination. And so those aspects make it an integrating system.
And so as we began to test our system, these are the results that we came up with. We started off with an IMC correlation. We came up with a value for our gain of 0.05. So if you look in the top left graph, you can see how our rudder position changed over time. It oscillated slightly before reaching a more steady value as we approached a more constant angle of travel. As you can see in the bottom left graph, this is our position over time. You might see this bowing out to the southeast direction. That correlates with the water current that we put into our Simulink model, that disturbance. It's a major disturbance in this case because our current moves almost at the same speed as we would expect our sailboat. But looking at this graph, we decided that we could probably achieve a more direct route. We could also probably get rid of this little oscillation there at the end as it reaches its final destination. And so in order to do this, we tuned our controller and we arrived at a gain of 2 radians instead. And by doing so, we found that our tiller controller moved much more rapidly and had much less oscillation. And also we found that our XY coordinates, our position over time, was a much smoother graph. We got rid of some of that bowing out and all of that oscillation at the end. Additionally, we wanted to point out that our sail angle is very important to speed, and so as we arrived at our destination, we wanted our sail to transfer less of the energy provided by the wind to our boat, so that eventually we could come to a stopping point at our final destination. And so where you see it on this far right graph, this vertical line is the point where we are arriving at our final destination, and our sail angle is going to zero in relation to the oncoming wind. And so just for final conclusion recommendations, our controller is capable of sailing to a set point destination. And on our previous graphs, you saw that curve because of the water current. Also is a P-only controller. So for our future work, we would wish to develop a model to predict the effect of the current, and to effectively remove that bowing and provide us a straight line from point A to point B despite the water current. We also would wish to use this model in a controller to plot a more direct route to the set point destination, regardless of wind also.
Thank you.
Thank you.